In the 1970s, most computers were as big as a room, they were super expensive, and they required people in pocket protectors running around to keep them working. There also just weren't that many computers overall, so people had to share them. The way this usually worked was using a device called a teletype, shown here on the left. The teletypes were wired to the computer, and you would type messages or instructions in on the keyboard, and the computer would send back output that would get printed out on the printer. This was basically the predecessor to modern terminal applications. The University of Minnesota had a handful of computers at this time in the mid 70s for faculty, staff, students, pretty much anyone on campus who wanted to use them for any purpose: programming, instruction, playing games, or doing scientific research. This is the newsletter from the University Computer Center from 1976. It shows the schedule for when the computers were in operation, when they had those pocket protector people to keep the computers running, because they couldn't be running all the time. And then it shows the sites around campus where they had teletype machines or remote job entry sites where you could turn in a stack of punch cards that would then get fed to the machine. So remote jobs were things where you would submit them and come back the next day to get a result, and the time-sharing labs were more like interactive computing where you would use a teletype machine like this. And these teletypes weren't just on the UMN campus itself, but there was a network of them all over the state of Minnesota at various colleges, universities, and some public schools as well. So this was pretty cool that Minnesota had this in the mid 70s. Computing was pretty accessible to people all over the state, but most of the computers themselves were located in one place. And the place where those computers were was the University Computer Center in Lauderdale, Minnesota. This is just across the border outside of Minneapolis in kind of a nondescript industrial area. Most people driving by probably didn't know that it was the center of educational computing in the state. Now, at the time, Minnesota was better than most states at this kind of thing. There were a lot of policies in the state to foster public computer infrastructure, especially for educational purposes. This is a case study from a 1982 congressional report calling out really that Minnesota had a goal of not only just having computers for educational use, but offering equal access. And from there, it was kind of obvious that the way to achieve this was to have centralized computing infrastructure sort of for economies of scale and to make it easier to operate and maintain the machines. And so these communal computers just kind of made sense for this purpose. One thing to come out of this was MEC, or the Minnesota Educational Computing Consortium. MEC is best known for Oregon Trail, the incredibly popular video game, and they had a lot of other software, and they were probably one of the best successes from this policy. So before you could play Oregon Trail on a screen, students would crowd around, like you can see here, and play it over a teletype machine that were installed in their schools. So if you were lucky enough to be a student in Minnesota in the 70s and be at a school that had one of these teletypes, you could go up and play Oregon Trail and see "You have died of dysentery" printed back at you on a dot matrix printer, while the game itself was running on a UNIVAC that looked something like what you can see on the photo on the right in the Lauderdale Computer Center. Then the 1980s came, and personal computers like the Apple II became way more ubiquitous, and a lot of things that used to require a centralized big computer to run could then be distributed as software to run on a desktop computer. Meanwhile, there was also growing use of computers in scientific research. This is a whole newsletter from the late 70s in the University of Minnesota system for computing in the humanities, where they were doing all sorts of things like linguistic analysis and just kind of showing the diversity of ways that researchers were using computers. One thing to note about this time is that instructional use of computing was subsidized, so a lot of times class instructors didn't really have to pay much, but research wasn't. So professors and departments that wanted to use computers in their research had to budget that into their grants. Even still, there was a ton of demand for computers and ever increasingly powerful computers for research purposes specifically. And this brings us to 1981 when Mech and the other computers in the Lauderdale Computing Center got a new neighbor, the Cray 1B. The Cray was a huge leap forward in computing hardware for the university. It was 20 to 40 times faster than the other computers that they had, and it was actually the first supercomputing class machine to be acquired by an American university. It ran at 140 megahertz and had 4 megabytes of memory. This is also the famous sofa computer, so they had these nice padded cushions around the perimeter of it where you could sit, and it would probably keep your butt warm while it was churning away. But to really get a sense of the beauty of this machine, you got to see it in color, because when they ordered it, this was serial number 12 of the Cray 1B series, they had it finished in maroon and gold to match the university's color scheme. So in some way, this Cray was just another computer acquisition for UCC, but it did kick off a whole split of dedicated hardware ops organization for research use specifically. And so if researchers were doing something on a personal computer or on the more general purpose machines and needed more processing power, more storage, they could shift their work over to the supercomputer. And so since 1981, it's had some name changes, but there's basically been one organization within the university that's been the home for supercomputing and expertise to help researchers run their research on the supercomputer, and that is the Minnesota Supercomputing Institute, or MSI. I work at MSI, I'm a software engineer there, and that's kind of what brought me into this and got me interested in this. And MSI has been around ever since. But just to be clear, even though I'm speaking from my experience there, I'm not representing the University of Minnesota or MSI in this talk. Now let's pause for a sec just to talk about how I think about computing infrastructure. Now, infrastructure, as I think about it, underlies our ability to use communal computers like a supercomputer for many purposes, like for building applications on top of, whether they're web apps, mobile apps, or for doing other things like science. This is kind of a natural boundary, so whether this is happening all in one organization or separated where you're renting computing time from an outside service, this is kind of like a natural boundary because you have the people with pocket protectors working on the infrastructure level, and then the people who are a little more concerned about what the computer is being used for, who are handling the stuff you're building on top of it. This can look a little bit different for apps and science, but ultimately what they both need from the infrastructure underlying it are a few things. They need CPU, they need the actual computation to do something useful, they need storage, they need a place to store data, to write output to refer to later, and they need some way to connect the computing infrastructure with the outside world. In the context of apps, we usually think of this as the cloud, and in science, we usually think of this as the supercomputer. So these are kind of abstractions. You know, there's a saying, the cloud is just someone else's computer. That's kind of what all this is getting at. There's not really any magic here. It's just kind of the abstraction that we use so that we can not have to think about everything going on under the hood. Now, I'm sort of an apps person, but for most of my career, I have a little bit of infrastructure experience as well, and I suspect that a lot of people watching this are kind of in a similar boat and don't know quite as much about what goes on the science side of things. So I want to take a little bit of a diversion to talk about what is it that researchers do exactly. Now, the way I think about this is a scientific researcher is ultimately trying to produce some sort of research output, which usually gets published in a paper, presented at a conference. And the two kinds of ways that that can look are either testing a hypothesis, kind of trying to get an answer to a specific question that they have, or producing a data product. And this is usually something like taking some raw data, going out in the field, collecting data, and packaging it up into some format that's more useful for other researchers to use to then test a hypothesis or produce additional data products on top of. So how do they use computers to do that? One category of what this could look like is modeling or simulation. So this is kind of, you have a model of how something in the world works or some physical phenomenon, and you need to use a lot of CPU to churn through that model to perform a whole bunch of calculations to produce a result to give you some simulation of how things would work according to your model. This also comes up a lot in math and computer science, trying to kind of proving the correctness of programs, proving that certain properties of numbers or that kinds of thing are correct. And then another category is data analysis. So this is where you start out with a lot of data, and this could be imaging data, genetic data, human activity like economic or behavioral data, and then you do some analysis on it to understand or extract some meaning from this raw data. So this, in addition to requiring that big CPU, generally also needs a lot of storage because you're working on a lot of data that needs to be kept somewhere. And then another thing to keep in mind is that unlike a web application or a service that's kind of running in perpetuity, when a scientist is using a computer, they're ultimately just trying to get a result. So what that means is they'll write code to kind of get that result, but they're not keeping something running once they get the result. And this kind of gets into like how scientists write code. A lot of scientists do write code. They have deep domain expertise in software libraries that are usually specific to whatever they're studying, but they're not writing what I would consider production quality code. So we love our research partners, but they're not software engineers. It's kind of a different skill set. And what that also means that there can sometimes be a little bit of a bigger gulf in understanding between the scientists and the underlying infrastructure people in terms of understanding what's going on under the hood. Now, here's just one example of the sort of research that was done on the supercomputer in those early days in the 1980s. This is a beautiful graphic representation of a process called stellar convection, which is where gases of different temperatures are mixing in the atmosphere of a star. And this is something that two astrophysicists at the University of Minnesota produced on the university's Cray one in the mid-80s. There's a really cool print of this in the MSI offices. As more and more researchers started using the used supercomputing infrastructure, this got the attention of the governor of Minnesota at the time, who started seeing this as a strategic advantage to kind of invest in more to keep researchers in the state. So as I mentioned earlier, academic or instructional use of computing was subsidized, but research use was not, which actually led to a situation where researchers started leaving the university for other institutions, both universities and government agencies, where they could do their computation-heavy research without having to factor those costs into grants and budget for it. So this kind of became a factor in the legislature wanting to get more funding for supercomputing. There was a lot of pressure to build out this capacity and really not get left behind during the computing revolution as it was affecting scientific research. There was a plan to build a $50 million facility to get money from state and federal agencies, and that didn't really pan out. But instead, what wound up happening was the university wound up spinning off the supercomputing infrastructure into a private subsidiary. So it was actually a private corporation into this other building they called the Minnesota Supercomputer Center. So the idea of this was that they would not only, as a private company, they would be able to not only serve the university's supercomputing needs, but also sell services to other private businesses and agencies that needed this infrastructure. This was actually kind of a drastic move. It ruffled a lot of feathers at the university and at MSI in particular. It led to the director at the time leaving. But they did get their new building. They moved the Cray and started acquiring other supercomputers. This building is still around. It's right off of 35W at 1200 Washington Avenue South. It's got a pretty distinctive facade, and you can see it sort of going into downtown Minneapolis. They had a really cool machine room inside. Kind of has like a 2001 Space Odyssey vibes to me. So at this time, there were over 200 researchers. using these resources. And there were MSI staff, so this was like university staff that were co-located in these facilities with the private MSC, which was like the private company. But the company was still kind of calling the shots and dictating kind of what they were acquiring and who got to use it, even though most of the money was actually coming from the U. And this was a cool annotation that I found on this website, crayhistory.net, where they're kind of showing all the different machines that they had in the data center. So the Crays and the Cybers, then CDC, those are the supercomputers, and then the IBM and the VAX are more traditional mainframe computers. So they had a pretty good collection of resources there. So, but as I kind of said, there was some tension here between the public-private partnership, and this all kind of came to a head in the early 90s, where there was this pretty scathing report that came from the Minnesota State Legislative Auditor. They claimed that the Minnesota Supercomputing Center, the private company, was operating with considerable secrecy, that they gave their commercial customers preferential treatment over the needs of university research, and basically just said that the university didn't even have the level of transparency needed to determine if they were even getting a good deal on supercomputing services through this subsidiary. Initially, the university pushed back on this report. They basically said, you can't show that we're doing fraud, so everything's fine here. But in the years after that, the U did start unwinding the MSC arrangement and started to bring supercomputing back under more direct management of the university. Part of that meant moving out of that MSC building and moving the equipment out of this beautiful machine room, which today is home to the Minneapolis Pickleball Club. So pretty cool reuse of that space. And as for MSI itself, it moved into Walter Library in 2002, where it's been ever since. Walter Library, if you're familiar with the U's campus, is right on the main East Bank. It's the main science and engineering library. It's got a beautiful reading room that's best known for having hundreds of carved owls all over the interior decorations. My office is in this building, but it's on the upper floors that aren't nearly as ornate as this. And the data center, where the supercomputers live these days, is in the basement of Walter Library, but I've got to say that space is also a bit of a step down from the MSC space. And we'll get a look into the data center in a second here. But first, fast forwarding to today, I wanted to talk a little bit about the research that we do at MSI. A lot of different research groups use our resources. We have about 1,250 different labs, sort of professors sponsoring entire projects using our facilities for all kinds of research. You can kind of see a breakdown here by research group. And this is not just for the University of Minnesota itself, but we also have a mission to support academics around the state. So there are other institutions that partner with us. Just kind of speaking to our impact, we have our hands in a lot of research that goes on at the U. Almost half of the grant funding that comes in for research at the U goes to users of MSI. Hundreds of papers are published in top journals every year from research that use our services. And one other thing to note is that we aren't affiliated with any one department or school. We're under something called the Research and Innovation Office. So this houses a lot of units that provide shared infrastructure and expertise to assist researchers across the university system. Getting into some of the major users of MSI, a couple big ones are the U of M Genomics Center. So they do a lot of gene sequencing work and analysis of genetic data using our systems. The Masonic Institute for the Developing Brain is another major partner. We have a lot of projects with them, and they use our systems for a lot of MRI data and analysis of brain data. And some other fields of research that see heavy usage of the HPC systems, a lot of climate and atmospheric research, so that's like modeling of the Earth's atmosphere and predicting climate effects and weather. And then another interesting one is health insurance data. So one of the largest users of storage at MSI is actually a group of health economists that take data that is required by federal law to be public on what providers charge various health insurance companies for different procedures. It's a huge mess of data that we have a team and a coworker of mine that's built a data pipeline to pretty much just process all this data, deduplicate it, and get it into a format that other researchers can use to actually understand how our healthcare system in this country works. Just a little bit more on the research we do at MSI. There was a research exposition for research computing just a couple weeks ago that I got to go to. So they had a bunch of grad students who had posters set up in this room. And one of the interesting ones that I saw was the study where someone came into the hospital with an unknown infection. They ran a culture of that infection through a gene sequencer, copied the raw data into MSI, and after a couple days of computation with a few different software packages, they were able to identify 2 novel bacteria strains that had never been seen before. So just kind of another example of the cutting edge research that happens at MSI. Now, professors can get onboarded to MSI pretty easily. This My MSI portal is a part of what I work on there. And so anyone at the U can log in with their single sign-on university credentials. We check their role through HR systems, and eligible faculty can get access to the systems right away without any manual approval step. So it's pretty quick to get them onboarded. Research groups have access to up to 20 terabytes of free high-performance storage, and there are no hard limits on how many jobs they can submit or the amount of computation they can do, although we'll get into the details of what that means in practice shortly. Shifting over to how MSI itself is structured, we've got about 60 staff. Half of those are analysts or research informatics staff. These are basically kind of like consultants. So this is sort of like an agency model where a research group will basically be paying for their salary for some period of time while they're working on a project. So these are generally grant funded roles. A lot of these folks have PhDs and they're experts in certain fields so that they kind of can connect the dots between the technology and the studies that the scientists are doing. Then we've got about 20 engineers who are kind of in the operations, security, and actually working with the bare metal servers. That's kind of the folks that are really keeping everything running in the machine room and the software on the HPC systems. Then we've got a handful of help desk folks. They're really great. They do a great job just being the first line of defense for any kinds of questions or issues that come up from our users. And then my team is the application team. There are 5 of us, and we're split similar to analysts. Some of us work on external projects, and just a couple of us work on the internal, more custom systems where we're a little more integrated with the ops team. So I'm one of the few engineers that in that team that actually kind of work on both sides, both external science projects and the more internal operation stuff. Now we can finally go down the stairs and into our humble data center, and I'll fill in some of the tech details of how all these pieces fit together, and then we'll wrap up. So this is a floor plan for the B40 data center. This is about a 1 megawatt facility, which is pretty small potatoes in the scheme of data centers, especially when you hear about hyperscaler AI data centers. A lot of those are usually talking about 100 megawatts or more of power utilization. So 1 megawatt is like 1% of those kinds of data centers. So just to kind of give you a sense of scale there. I'm basically going to be talking about the 2 main clusters of racks in the bottom half of this slide. Infrastructure systems on the left, which has sort of general purpose servers, the storage systems, and then the Agate cluster on the right is the actual HPC system. So for some of these, I'll have the map. This is kind of rotated on the left. The entryway where we're looking now is at the bottom of the screen where that arrow is, and we're kind of looking down those aisles of racks. As we walk into the first cluster of racks, we get to our first system, which is primary storage. This is also called the VAST, which is the vendor that we use for some of this hardware, and they have kind of a proprietary system for handling some of this stuff. This is basically a big fast file system. We have 12 petabytes of available storage. This is all solid state disks, so it's very, very fast. This is where user home directories live, where project storage, so that's that 20 terabytes or however much storage each project has. And these file systems are mounted in pretty much every MSI system, so you can kind of access it, access any files that your user has permission for. And one thing that kind of blew my mind is that all of this is just managed using basic Unix user group ownership permissions. That, it's a huge amount of data, but this is really what Unix was designed for, these multi-user systems where many people are logging into the same systems and need to control access for who can read and write what. So that's basically how all of this primary storage is exposed. And then we also have a quota system, which is implemented through VAST so that users can't write more data than they're entitled to. We do give our users some extra visibility into their storage usage, so a project can see which users in their project are using the most storage, how old the files are, because we really want, this is expensive solid state storage. We want this to be mainly used for data that is currently being actively used in research. So if groups have older data that's just kind of sitting around, we really want to help them surface that so that they can move it to less expensive tier 2 storage, which, speaking of which, that is the next system that we get to as we're walking down this aisle of racks. Secondary storage is also called Ceph. That is an open source project for distributed storage system. The main way that our users interact with this is through an AWS S3 compatible API. So it's more like object storage than a basic file system. And we have even more capacity here. We have about 30 petabytes. And this is also obviously all duplicated. It's kind of like RAID, but it uses a different system that's a bit more efficient and can handle more drive failures safely. And this takes up about 5 racks. And we have 2,700 spinning disks. So this is less expensive because we're using spinning disks instead of SSDs. Also, just kind of as a point of comparison, if users need more than their allotted secondary storage, we charge research groups at the U $33 per terabyte per year, which is about 10% of the cost of AWS S3. So it's subsidized, but even the unsubsidized cost is substantially less than what S3 charges. Plus, it's way, way faster if you actually want to use it in the HPC systems. And this is how you get so many disk drives in such a small space. We have these chassis that can stack them 2 deep. So this, in a 2U rack space, can hold 24 disks. So I thought that was pretty cool. Next, we will move down into the agate cluster itself. So this is my coworker, Edward, who was kind enough to let me into the data center because that's not normally part of my work obligations. And this is the actual supercomputer. So that we have a lot of fast CPUs and GPUs. There are about 500 nodes in here, just under 500. Most of them have 128 CPU cores and half a terabyte of RAM each. And overall, this agate cluster has about 8 to 9 petaflops of compute capacity, which the top 10 supercomputers in the world are 50 times or even bigger than that, but still 8 to 9 petaflops. We don't participate in the top 500 rankings. That is kind of the standard for ranking supercomputers globally, but if we were, that would put us somewhere around the 200 position in terms of supercomputers in the world. So most of the way that people interact with this is through batch jobs. So they'll submit a job through, there are a lot of ways of submitting jobs, command line, there's a web UI, and some other ways of doing it. So you submit a job and they kind of wait in the queue. We also have some capacity for interactive jobs. So this would be something like a Jupyter notebook or something where you're kind of doing more interactive processing in a more real-time environment. So various software packages have support for that as well. So how do we actually run all these jobs and manage all these different workloads without having to have hard limits on our users, like I mentioned earlier? Well, we use something called Slurm, which is a very popular manager of HPC workloads that a lot of centers like ours use. And it has something that's called a fair share scheduler. So basically what this means is everything's kind of managed through a queue. Users submit their jobs and we track recent usage on a per group basis. So if a group has been using a lot of our resources recently, then they'll kind of get bumped farther back in the queue. So groups that haven't been using as much can get priority. So basically this allows the system to kind of self-regulate who gets priority. We don't really need to dive into it and mess around with this too much. It kind of just works itself out. But we do keep track of overall utilization. We have different partitions where different hardware is assigned so that we can have small jobs that don't get hung up waiting behind large jobs, and then different jobs that have certain resource requirements like high memory or require GPUs. They can be scheduled on the servers that actually have those resources. And so we aim for about 80% utilization across the cluster, and we generally are able to stay around that for most of our partitions. So the newest addition into the Agate cluster is some NVIDIA H100 GPUs. These were the top of the line general purpose GPUs when they came out a few years ago in 2022, which is when we acquired them. I thought this was kind of funny that there's actually a listing for the H100 on Newegg. So if you had $30K to spare, you could get yourself a top of the line GPU. I mean, there are newer ones around these days, but also you actually can't because this is out of stock everywhere. OpenAI and the other big hyperscale compute companies have bought up pretty much all of this stuff, and it's pretty much impossible to get this top of the line hardware anywhere. So good luck with that, but we have ours, at least a few of them. Now, a quick word on heat management. We have these glass doors kind of separating the cold zone and the hot zone in the data center. So the way this works is we have cool air-conditioned air coming up through vents in the floor, and then the air gets pulled through the server racks, and where it accumulates a lot of heat because servers are very hot, and it gets exhausted out the back. So the inside of this cold aisle and the outside are different by 20 to 30 degrees. So it's pretty noticeable. And then this is just the air cooling. We also have liquid cooling. So these are this is glycol systems that run into those H100 servers, and there's a heat exchanger that sends this heat into the university's chiller loop. So we actually kind of have a central heat sink that we're able to deliver some heat into, and then we also have some liquid to air heat exchangers like these fans on the right that kind of take some of that a different cooling system that transfers some of that hot water from the servers into the air. Now, how do we keep all this stuff running? So just a few kind of points on this. We do have a monthly maintenance day. So once a month, the cluster and most other systems will get rebooted. So we do take a couple hours of downtime every month. This is really not a huge deal. Our users know that it's coming. A lot of the work that the operations team does is reactive, so handling hardware failures, adjusting things based on changes to how temperature is managed, installing security updates, software upgrades, and just dealing with user issues. So my coworker on the ops team said that the biggest challenge that they run into is users, because users will always find interesting ways of using our resources, and we need to kind of make sure that whatever they're doing doesn't affect the performance of our systems for everyone else. We use Puppet, which is a configuration management system, to basically keep all of the operating system and system level packages and configuration up to date. So the config for all that is stored in Git, so we can kind of do normal code reviews, Git ops kind of thing, but works a little bit different than something like Kubernetes. And then everything runs Rocky Linux, which is a Red Hat derivative. So that's just kind of a bit of a high level overview of some of the operations details. Now, finally wrapping up with what is coming next for MSI. We've got a lot of stuff on the roadmap. Can't really get into all of it here. But one thing that we're working on is getting a regulated data cluster up and running. So this would be able to handle data that is regulated by laws such as HIPAA for health data. This has been a lot of sort of compliance checklists, things like that. There are other places at the U where researchers can have access to HPC resources that they can use this kind of data in, but MSI just is better, and so they've been really asking us to get something like this up and running so they can use our systems for more sensitive data. We're also working on streamlining some of the resource provisioning, so when groups need to purchase additional allocations beyond what their free entitlement gives them, a lot of that's pretty manually provisioned, and so I've been working on some tooling and automations to make that a little bit smoother for our staff. And lastly, we usually will do a hardware acquisition every couple of years, and so that was on the roadmap, or it still is on the roadmap for this year. But that's a little bit up in the air at this point. Usually we'll spend a couple $1 million on new CPUs, GPUs, that kind of thing. But with the price of computer hardware, with all of the hyperscalers buying everything up, a server that was quoted at 20K last year, we've gotten quotes for over 80K this year. And also a lot of our vendors, when they give us a quote, they'll only honor it for about 2 weeks because of how volatile prices are, which if you know anything about university procurement processes, 2 weeks doesn't really fit into how a university acquires millions of dollars of compute hardware. So still a little bit up in the air about what we're going to do on the hardware side this year. Which brings me to something that you may be wondering. Is anyone doing AI on the supercomputer? Well, there's not one answer to this, but some researchers definitely are running their own LLMs as part of their research. We provide the hardware and don't always know exactly what they're doing with it. We are seeing a few new projects coming in that are looking to use MSI's resources to kind of do a new line of research, making use of newer AI tools, but we're not seeing a huge influx of this. Most of the projects coming in are still kind of more traditional scientific methodologies of research computing. I think one reason for this might be that a lot of people going in that direction are not really coming to MSI necessarily. They may be going directly to commercial vendors, and the U also has a new unit called the AI Hub where they're not really dealing with the hardware side of things, but kind of just fostering, giving people who are interested in AI and education and research a place to talk about that and figure out how to go about it. So I'm glad those people have somewhere to go for that. That's not us. So kind of wrapping up and putting a bow on all this, supercomputing is definitely different from what you may be used to as a computing environment, but it's really not all that different. It's all kind of just the same pieces arranged slightly differently for a slightly different use case. Collective compute infrastructure, meaning big computers that a lot of people are sharing, that's kind of been the norm for the most of the arc of history of computing. And personal computers are a little bit of an aberration from that, but there are a lot of ways of structuring these collective compute resources, and the way that's structured and who owns it and who operates it really matters. In particular, for-profit corporations are generally going to be a lot more extractive and not necessarily provide the same level of service for the cost especially for socially useful things like research. And Minnesota overall has been pretty good at offering this kind of common good compute infrastructure, not just on the supercomputing side, but kind of farther back into the past as well. And I really think this is an interesting model for us to keep in mind, as we're thinking about computing sovereignty, wanting to make sure that we have ownership of our data, that we aren't blocked into walled gardens by Google and the like. And as we're kind of wrestling with the advent of expanding AI data centers all around, there are lots of ways of building up compute infrastructure, and we don't kind of need to take the private corporation's vision of how that's going to look at face value. So that's about all I've got. One last thing before I sign off, though. If you've made it this far and you are staff at the U, we are forming a union with SEIU Local 284. You can visit this website to learn more about that. We're organizing IT workers, marketing communications, and a couple other job categories. So if you're interested in learning more, follow that link. And thanks for watching this video.